completed lecture 2, right?
Yeah.
Completed lecture 2.
Just
What is
trying.
ND?
It's the density of donor atoms.
Donor density.
The donor density.
Yeah.
Percentage human and for mobility of electron.
Is it mu known as the mobility? Mu
Yes.
n.
Yeah, it's mobility of electrons.
Huh?
It's the mobility of electrons.
This is the one, right?
Yeah, that's mobility of electrons, and mu
Is
p is
this
mobility
mu?
of the holes. Yeah, that's mu.
Mu n, right?
And small n.
Mu. This is
And mobility of atoms.
this is mu np.
It's like, I think it's like 400 and something, 480, is it? I don't know.
500.
500. Okay.
Yeah. You can see it here if you want.
Oh, is that for the problem?
Yeah.
Okay.
Charles Q.
Alright. I did
You've
that
done
already.
602.
1.602.
Times 10 to the negative 19.
I think it's
Negative 19.
Can I take a peek if you don't mind of this?
sure, yeah.
Okay.
There are four
Actually, I'd
steps
rather
in
you not
this.
take a picture of it.
First, find the
Thank you.
density of electrons.
Yep.
Density of electrons. The formula to find density of electrons.
Equal to ND, correct?
This is N type.
Oh, NI.
Ni plus N
Yeah.
plus N.
Equal. This is
What will be the value for this?
equivalent ND.
2 times 10
The density of electrons is approximately equal to donor density
Yep.
in our case. Reason? I-
Because the donor density is significantly less than
It's
the.
an N type.
It's the entire, yeah.
It's an N type.
So we
The value
just
will be
2 times 10 to the 19.
the same value.
Yeah.
we write this value and tell because of the n-type semiconductor, that's why it is
Yes.
ND.
And
The donor is the main
N will
electron.
be equal to N.
Okay. The donor density is higher in this case in the n-type semiconductor, so the value will be go to ND.
Mhm.
Yes.
So that's the reason it's 2.1
So if it is p-type semiconductor,
then
N.
NN or N is it donor
P-type semiconductor, N is
don't NR or PP for P
PN.
PP.
Well, the problem asks for PN, but he's asking for
For
PP.
p-type, for p-type or not. So it's just PP is a representation. N.
Is the same equation, right?
Yes, this is the same problem from slide 17 lecture.
Oh,
And how to find density of holes? We have density of electrons, density of holes, En.
Intrinsic.
so we have
squared divided by
NI.
a D.
So we have NI from here. Yeah, NN
N is squared divided by N.
ND.
So that gives us 10.51.
Did you, Dr. Chaudhary,
Did he? Because he said he was going to give us homework and then he never put anything up on Canvas.
He said practice.
So you already, how many of you did this one?
No, I didn't do that.
Okay. So we know the type.
I mean, I did this problem. I was just.
Consider acceptor donor
17.
N8, acceptor donor as 5 plus N. And mobility of holes.
What's that the N that you put on? Oh, that's the N.
This is for N or T. Acceptor donor.
No, there's no homework.
So you said NA is what? I'm sorry.
What is this NA? Which type of silicon is it?
Oh, P-type?
P-type. We are considering acceptor donor, mobility of electrons as 1200 and mobility of holes as 1200 and mobility of electrons.
Are you doing a different problem now?
Yes.
Oh.
As 400 and the charge will be same. What will be density of holes in this case?
So you're trying to figure out the answer to that.
This was in slides.
Yeah.
So it's a non-issue. As you already did.
I have a question.
We
Where
didn't-
do
we never went over it though.
yeah.
We never went over that problem. I was just trying to see if my answer was right.
This is P-type semiconductor, not N-type. These are not the slides. I have created this one.
Talking about the N type.
I just painted it like.
So I have a question. Ni squared. Where do I get it?
We solve this step by step. Find density of holes.
Yeah.
That's the.
Density of holes.
It's a constant for silicon at standard temperature. It's
What will be density?
1.45 times
The
10
same
to
problem.
the 10 centimeter
Dr. Chaudhary in slides, it's
per
N-type,
centimeter.
this is P-type. This is P-type semiconductor.
Okay.
Yeah, so that's a constant. That's known for
So
silicon.
P-type density of holes will be approximately equal to
Got it.
Equivalent to NA.
Yep. Na.
5 times 10 to the N.
What will be the value of NA?
5 times 10 to
Five,
the
five times. And next,
That's at
density
8.
of electrons.
That's 18. My fault. 18 on it.
Density of electrons.
Maybe Ni squared.
What will be density of electrons?
Ni squared divided by Na.
Ni squared divided by
Na.
divided by
Na.
the value for this one. Consider Ni
So is N on the is NI a constant? Oh,
It's 1.45 times 10 to the 10.
okay.
4, 5, 10 to the. Yeah.
Yep.
So is N on a constant or is that given in the
So
problem?
is anything wrong?
it's given in the problem.
Oh,
You told not to take the pick, so I was asking.
Value here 1.45 into 1.5.
Is anything wrong with it?
Ni equals to 1.45 into 10 to the 10. So they are taking approximate value.
Take the exact values. Give me the
No,
final
this
answer.
is-
What will be the final answer for
42.05.
40?
42.05
42.05.
centimeter.
Any other answers?
I guess.
Can I look into it?
N on
Could be
Per centimeter.
with units. get the right
And
should be per centimeter. What will be the final answer?
So this is also per centimeter cube. 1.5 into 10 to the power 10.
Yes.
Oh. 5.
will be 45.
Divided by.
What is the value of energy? Is it 1.44 or 1.5?
1.5.
It's
I think it's in the PPT, it's one.
It's the same.
Is it 1.4?
It's not written in there. It's not written in the value. The extreme will be asked for. The value.
Math is not mathing. 0.5 times 10
Yes. I will put it in the
divided
P type data. Half P type half.
It's in the slide. It's said 1.45.
1.45.
No, that's the wrong one. That's the wrong one.
Okay.
What will be the answer? 4.5 into 10 to the
So,
power 1? 4.5 into 10 to the power 1.
Dynamic density of silicon crystal is Si 5 to the power 10 to the power 22.
yeah, it would be 45 per centimeter cube.
1.45, right?
10.
Okay, whatever.
No, using the value that he gave, it would be 45
45. Okay.
per centimeter squared.
I didn't bring my calculator.
Using the constant, that's it would be 42.05. So they're relatively close. It's insignificant.
That's the final answer.
45.
45 per centimeter cubed.
Calculate conductivity. Calculate conductivity.
Uh-oh.
Yeah, you did.
So,
He
we
said,
want
Formula for
you got to go back.
conductivity is going to be
He don't want to back.
formula for conductivity.
Q times mu n plus mu p
He said,
mu oh I'm sorry I'm talking about the n type.
Don't get confused with exam. That's the reason.
Mu p. Right.
Mu p.
That's right.
I have a question.
yeah, the mu in. Oh, no. He's on P side. So,
Conductivity of p type.
yeah, it shouldn't be a U. I think that right.
This is P type. This is N type, that's why NN. This is N type, that's why it's PN. That's coming here. NP, PN. NN, PN. P, PB, NP. So it's NP. So I'm following the formula, that's what I mean. Because it's P type.
So that 45 cubic meters
45 per centimeter cube.
per, yes, cubic, yeah.
Per cubic centimeter.
Just created this. What to take on the slides?
Actually, he, in slide 10 of lecture 2, he doesn't specify that this equation is specifically for P-type or N-type. And he doesn't use PP or NP. He uses mu N times N plus mu P times P.
I think that's the general one, so.
Oh, I mean, actually, no, I guess this would be correct anyway.
Which
Yeah.
one? Slide 10?
Because if he's not indicating, I don't know.
Yeah, that's the general one.
Yeah.
So when there's a P type, you need to put PP.
Right.
When there's an
right,
N
right.
type, you need to put NN. That's a general type. General equation that you're seeing in the slide 10.
Right. Mu and oh, okay. And then yeah. Okay, you're right. Yeah. That's love how there's like a million different ways to write things.
There is no equation for P-type in PPT.
No, I mean, technically that's correct.
That's correct. He has given us.
It was
the
just
general
the
one.
notation.
You
There was a
put
notation
P
difference. Yeah.
And make it like for the formula for the P type and for the N type. That's why I came to you like this is the equation. You
I
just-
just created this one. That's fine.
Yeah, I know.
No, it's good.
But it
it's
makes
good.
more sense
Yeah.
now.
Yeah. It's more specific, which is helpful.
Yeah, that's why I
Um,
came to you and say, if this is the way.
So then we're gonna do.
Once if I understand the formula, it's very easy to solve the problem. Huh?
These equations are
Yes.
I've studied it, so I know some things.
Started with this, gave you
Times 10 to the
What
negative.
is the final answer for Panic?
Oh, I hate it.
38.45 into 10 minus 7.
I don't know.
38.45 into 10 minus 7. 38.45.
solve for
12.
electron density
10 to the power minus 7.
and hole density over here. And you use
Minus
those two
7
along with Ni
or 1 centimeter.
for silicon to find
We have
Approximately
charge,
965.
electron charge, and that Q that comes from electron charge Q is 1.602. You better know that.
Mine is also like 38 point
Which is going to be the other equal. 45. Yeah, that should be. 9600. And then 2012. Did we agree on a conductivity value? Did-
It's,
So was the conductivity 9600? Okay. So resistivity would be 1.04 times 10 to the fourth.
Could you post these questions and their answers on Canva for later?
yes.
Like the step by step, if you miss anything, if you don't mind. I was confused for the NI, like who told me that.
No, I just repeated this.
No. You created
It's
it,
not
but
from textbook or.
yeah, I know. But it is exactly the same. So I was confused. I forgot that NI is that 1.45 in the generative word 10.
Yes, no, I just came up with random.
Well, and the intrinsic carriers are dependent on temperature anyway, so it might not be 1.45 if the temperature is slightly higher or slightly
Yeah.
lower.
In most cases, it should be room temperature. So
Yeah.
it should be room temperature.
So K is equal to, it's 300 Kelvin.
Okay, so what's that 38.45? What is that for? Okay, that's the wrong one. Okay, the right answer is not 65.
It should be around this.
I think if you use 1.45 instead of 1.5, you'll get like 160 or 1 something like that. So it's kind of off 2 points.
Should be around 9. 9.
That's what I got. If you use 1.45,
Well, can you show the calculation? Last time also I it was like this point on like conductivity. The answer was
The same thing, I cannot solve it. I don't have the calculator. I have calculator in my lab.
He used 1.45.
I just used the 45.
Did you use the
Oh, okay. Easter, that's one.
Should be around 96.
for N3.
It's tough to calculate. This is minus, there's a 10 to the power minus 7.
Used the one. Know how to calculate resistivity 1 by 100. Step 2.
Yeah, yeah, it's just the reverse. Just
It's just true. So
Oh,
don't
1.4.
forget to bring your calculators during the exam.
yeah. I need to keep it in my bag.
Yeah,
Because
Yeah,
some
I
ask the
did
calc
1.5
from
as well.
I don't know if you are asked the answer, if you are asked the calc.
you have 45.
Yeah.
So I have that.
There is one more problem. Slide number 36.
Yeah.
Oh, that's the one I didn't
This is
think of.
also example for a class.
Here we go. All right, I'm just gonna throw this in the trash now.
If we do an example for P.
Okay. PMOS, we are going to do it.
Yes, I like it. So examples are, most of the examples from slides are on N. Consider PMOS transistor in 90 nanometer technology. And
19.
process technology
Can I close this one?
with W by L 6 by 2. W by L ratio as 6 by 2.
1919.
90.
90, okay.
gate offside thickness.
PMOS.
Interesting.
30 angstroms. And hole mobility.
Oh, 6 by 2, 3.
VGS minus 2.5.
Okay.
For this PMOS transistor, find IGS for VDS minus 0.8 volts and then VGS minus 1.4 volts. This is PMOS transistor.
That should be yes.
VGS. This is PMOS.
That's a centimeter square, right?
Yes.
Per square VS.
Since this is example of problem number 2, there are 2 problems in lecture. Problem number 2 is on PMOS.
Yeah, sure.
To solve this problem, you need to consider the relationship between VDS, VGS, and VTH for PMOS transistor. And for these 2 cases, provide answers in which region PMOS transistor is. Is it in linear region? Is it in saturation region?
We can calculate from here. We can calculate the saturation region and others.
Yes, based on VGS minus VTH
Oh yeah.
relationship between these and these. You can check problem number 2 from lecture 2. It's on MOS. This is for PMOS.
Threshold voltage.
Which region is proposed? If VDS is minus 0.8 volts, if VDS minus 0.4 volts.
What is the threshold voltage?
Threshold voltage, consider is minus 0.6.
I have a question. Do we need the permittivity to solve that problem?
Just a relationship between VGS and VDS.
For the current?
For IDS.
Is it something we should just look up, or is it?
For IDS case, for this VDS conditions, which region, if VDS equals to this and VDS equals to this, which region is provided?
So this is for PMOS, right?
PMOS.
Yeah. So what are the conditions for PMOS linear and saturation region? VSG minus VTP if it is less than VSG, right? It is what? Linear or saturation? Or
From
and then or let me write the other way. If VSD is less than this and VSD greater than equal to this. Which one is linear, which one is saturation?
First one is saturation.
First one is saturation.
No.
In PMOS.
In PMOS, no.
Substitute the values.
Yeah.
Just
So he actually played a trick with you. That is, VGS is minus 2.5 volt, right? That's what you read. So his VSG is what? 2.5. And he said VDS is minus 0.8, right? So VSD, because in PMOS, source is the highest potential, so that is 0.8 volt. So you have it here. Now, the threshold voltage he already gave you. VTP is minus 0.6, right? So the magnitude of VTP is what? 0.6 volts. So conditions are same for linear and saturation in case of NMOS and PMOS. Just the polarities are opposite, right? So you know the condition, you should be able to. Okay? So you know exactly, these are the questions you'll be facing in the next quiz. And this is the exam. Okay.
I was going to spend all morning reviewing this and ended up spending all morning troubleshooting my computer that just keeps crashing.
Okay.
We need to practice a lot.
Yeah.
A lot.
So
As I said, I have repeated, I think already more than 10 times. Spend a lot of time on lecture 2.
I thought you had mentioned that you were going to put something up on Canvas that we
Yeah.
could practice with.
Yeah. So
Okay.
we are actually he's going to, the practice is basically homework.
Right.
He's going to upload a homework. Actually, we talked. He's going to upload 2 homeworks, one on lecture 1, one on lecture 2.
Okay.
And then within 48 hours, he is going to upload the solution as well. So please practice all those problems by yourself first, and then look at the solution. Because in the submitted homework, everybody gets full mark as long as you submit it, because this homework is for you to practice and understand. And particularly the trick he played to you with VGS or VSG for PMOS, keep it in mind, right? If it is given in the VSG format for PMOS, it should be a positive value. If it is given as VGS format for PMOS, it should be a negative value because source is the higher potential in PMOS, right? Thank you.
I have a question.
Yes.
So, the problem you're giving to us, it's one-sided. Like, let's say PMOS or NMOS. Can I do at home, like change all the
Oh,
value
yeah. Let's-
myself? I
Yeah,
want to
definitely,
test myself.
Yeah.
Change all the value and do it in the PMOS
Yeah.
or NMOS.
I think that's where you actually you get more practice.
I'll just.
I know you're giving me one.
It's not like we have NMOS example in slides. I directly give NMOS example for homework or quiz or exam. So I've changed the PMOS.
Yeah,
PMOS
that's.
exam.
I want to practice both of
There will be
them.
not direct questions.
Yeah. So I want to practice both of them because both of them we need to learn. That's the reason.
Already this one is done. Now it's done. I will log it up. Oh, sure. Yeah, please. Okay. Before moving to lecture, further into lecture 3, let's quickly look at some of the important slides of lecture 2. So I know that some students have questions about derivation of IP characteristics, and also the terminal voltage we need to go very clearly. So for the MOSFET operation, for MOSFET like the things we are talking about, we have to basically know the terminal voltage polarities, right? It's very, very important for you to know. In case of NMOS, source and the body tied together, and they are tied together to the ground.
Yeah.
So in case of NMOS, source is the reference potential. So everything is measured with respect to source, and it is reference at ground. So every other terminal will be at higher voltage, positive voltage than source. So for that NMOS transistor to work, VGS, these two voltages are voltage effective at gate and drain terminal with respect to source. So this must be a positive value for NMOS to function. And the threshold voltage of an NMOS transistor is actually a portion of voltage applied to the gate. From 0 up to certain point, as you increase the gate voltage up to certain point, there will be no channel, and after that voltage, it will be channel. So the threshold voltage is actually a portion of gate voltage, and the threshold voltage for NMOS transistor is VTN. That is also a positive value. On the other hand, here also, source is the reference potential, reference terminal for PMOS. However, source in case of PMOS is connected to supply. Supply is the highest possible point. So every voltage with respect to source should be negative. But if I like NMOS, if I write VGS, then it will be a negative value. But if I write VSG, it will be a positive value because source is at higher potential. Similarly, if I write VDS for PMOS, it will be negative value, but I have to write VSD to be a positive value. But for PMOS, threshold voltage is a negative quantity. But in equation, we want to know the difference between VSG and this value, so it is always written in magnitude form because inherently it's a thing. So all the IV characteristics for NMOS and PMOS are derived based on these two terminal voltages. So IV characteristics means relation between I current and the V voltage. So this is the relation between drain current D with respect to gate voltage and the drain voltage. So IV characteristics of any NMOS transistor is a graphical and mathematical relation between the current that is coming out of the drain and the two terminal voltages VGS and VDS, not the individual voltages VG, VD or VS. It is the relative voltage between gate and source and drain and source. So you have to keep that in mind. Now let's look at the step-by-step derivation of the current equation or IV characteristics. So at any given point in the channel length L is 0 here at the source end. Channel length L is the full value L at the drain end, right? Because everything is measured from the source end. So the length of the channel is a variable we are considering as a Y. It is 0 here, it is L here. So if I want to calculate current at any given point Y along the channel, first I need to know how much charge that is crossing that point in the channel, because current is charge flowing through a particular conductor in time. right? If it is a long channel, so at a certain point, through this point, at what rate charge is crossing, that is current. Current is measured in ampere. Ampere is equal to Coulomb divided by time. Coulomb per second is ampere, right? Basic electrical circuit 101. So to calculate the current that is flowing from source to the drain and going out, I need to know what is the charge density here and how much time it takes to travel from source to the drain. So at any random point y, the charge density in the channel, let us say it's Q of y at point y, will be effective capacitance at that point multiplied by effective voltage. So the effective voltage, we always subtract threshold voltage from that, because up to threshold voltage there is no channel, there is no charge density. Charge density appears when a bunch of electron in case of NMOS or a bunch of hole in case of PMOS gathers forms the channel. Until that there is no charge density. So we have to subtract that Vt from the effective or active channel voltage. So that VGC, that active channel voltage is what? It is the result of two voltages active on the channel. One voltage is the gate voltage, the other voltage is the drain voltage. So drain voltage along the channel, it has different value at different point. At point y, that drain voltage is V of y. So the active voltage across the channel is equal to actually gate voltage minus V of y, the value of drain voltage at point y. So forget about the negative sign first. So the effective channel voltage at point y is VGS minus V of y, and then we have to subtract threshold voltage anyway. So now, so that is my charge density. Since capacitance COX is a per unit area capacitance, by definition it comes from technology data sheet across the channel. So this Q will be giving us per unit area charge. If I can now divide it by time, I get the current. Now in the second line, why I added a minus sign and I added an subscript n with Q of y. Because we are talking about NMOS transistor, the charge that is accumulated here is a negative charge. So the amount of charge per unit area that is accumulated, it's a negative quantity because it is due to electron. That n indicates that it is electron charge, negative charge. One electron, one negative charge. So minus US, and then instead of gate channel GCC, I wrote the whole thing VGS minus VY, right? So that is the channel charge density. So I have explained that what is the effective voltage across the channel. Now, simple definition of current. Any current I is equal to charge divided by T. Now, think about it here. This Q of y is one we calculated per unit area charge. Because I have multiplied by COX. COX is by definition is the per unit area capacitance. Yes.
So this is Qn. If we go to Qpy, then
that will be plus.
that will
yeah.
that will be plus.
Yeah. And then you have to also change the voltage for
VSG.
Yeah.
And everything is the same. Right?
Everything is the same.
Okay.
And instead of VT, you have to write VT magnitude.
VT.
Right? Yeah. Yeah. So you can actually do the same practice at home for PMOS.
Yeah.
So now we are talking about, when we are talking about current, current is the total charge passing through per unit amount of time. So the total charge, let's say total charge is Q, capital Q, divided by time for the charge to travel from here to here, Q divided by T. Now the total charge Q is what? Charge density, that is per unit area charge Q and Y, which we calculated in the previous slide, multiplied by the total area of this channel, which is length times width. So charge area which is W times L times Q1 of Y. And Q1 of Y, we know that, we calculated. This is the Q1 of Y. In case of PMOS, as you said, it will be a plus sign, right? There will be no minus sign because we will be talking about hole density. So now that is the total charge Q we calculated. Now how much time it will take for any electron to travel from here to here? Very simple. The distance divided by velocity is the time for anything. So now we don't know here what is the velocity of electron. But from fundamental physics, we know that an electron will travel through a particular medium, conducting medium, at a speed that will be determined by the mobility of electron in that medium multiplied by the electrical field applied on the electron. So we know that electrical field we can calculate. So now we know that velocity v is mu n, which is the mobility of electron in the channel, multiplied by electrical field applied on the channel. So current ID is minus Qn y e, right? So I have replaced Qn with, so this is what I got as the current. I just replaced the value of Q and value of T, right, into that ID equation, and we got this equation. So this is the general expression of current ID through a channel, NMOS channel, at any given condition. Now as you can see in this equation, the variable here is Vy and the variable here is electrical field, because you have the lowest drain voltage here, you have the highest drain voltage here. On the other hand, gate voltage is constant from here to here. So electrical field is result of these two things. So the electrical field will be the effective voltage across this channel per distance. Electrical field is voltage per unit length. So electrical field is, electrical field, if you have a voltage, let's say in the direction Y, if you have a voltage V is applied, electrical field is dV over dy. Rate of change of voltage per unit length is basically voltage per meter is the electrical field, the basic definition. So now what we did here, so we'll keep it that. Now let us now define some condition, because this is a general condition. We know that VGS minus Vy minus Vt equal to 0. When this thing happens, then pinch off starts. So where pinch off will start? When Vy is the highest, that's where pinch off will start first. So Vy is highest as the drain end. Vy is the variable drain voltage. So VGS minus VDS, when it becomes equal to 0, then pinch off starts, and that voltage we are calling it saturation. So if the drain voltage is equal to or greater than this voltage, it is in saturation. If it is less than that voltage, it is in linear. Before moving further, we are first setting the condition for linear and saturation region. Now we have to replace that E, which is unknown, and we have to replace that V of Y, which is unknown. We want to calculate the current in linear condition. Applying that linear condition, we want to calculate current in saturation condition. Applying that saturation condition, what we will just derive here. So now as you can see, current E, as I said, electrical field E is dV over dy. Now, basic definition of electricity direction. If electron always flows in the opposite direction of assumed electricity direction, right? We know that if electron flows in this direction,
Correct.
we assume that positive direction of current or electrical field is in this direction. Here, we are talking about a voltage and electrical field in this direction for NMOS. But electron actually is opposite direction, because the current direction, assume current direction electrical field is opposite of, so actual electrical field E in this case will be minus dV over dy, because we are talking about electron flow, which is assumed to be opposite of the electrical field direction. So now I replaced E with dV over dy minus dV over dy. There was a minus sign at the beginning, so with E's negative sign, that minus sign cancels each other, right? So I just removed, in the original equation of I, there were two unknowns, Y unknowns and E unknowns, right? So by applying the definition of electrical field and taking care of its polarity for electron case, in PMOS it will be positive. In NMOS it's a negative electrical field. I cancelled out the negative sign. Now I have an equation with only one variable, Y. VGS is the voltage you applied, COX is a constant, mu is a constant, W is a constant, threshold voltage is a constant. Only thing that's remaining in this equation is Y. So now there is one variable dV, another variable Y. Now let us do some algebraic manipulation. Take this one to this way. So this side, Y, is a function whose limit value is when Y equal to 0 at the source end, Y equal to L at the drain end, right? So this side, if we can solve from 0 to Y. On the other hand, Vy, at the source end it is 0, at the drain end it is the highest drain voltage VDS, right? So the variable limit for this one is 0 to VDS, this one is 0 to L. So now if I do a finite integral of this from 0 to L, this from 0 to VDS, this is the exact equation I get. Of course, I skip few steps of integration, assuming that you know how to do basic integration. So this is called the linear current model, or IV characteristics. It tells us the dependence of current on the gate voltage and on the drain voltage. And for smaller voltage of drain voltage, smaller value of drain voltage, this will act as a linear, because as you can see, inside the bracket there are two terms containing voltages. One term is a linear term, right? The other term is a square term. But we are calling it a linear voltage. Why? When drain voltage is small, less than 1, if you make square of a fraction, it becomes a smaller value. So compared to, for smaller drain voltage, compared to this one, this factor will be very, very small. So the current will linearly increase with the increase of gate voltage and the drain voltage. So that's why we are calling it linear region of operation, and this is IV characteristics or current equation in the linear region. Now, we know that at the beginning of saturation region, VGS minus VDS, drain voltage will become exactly equal to VGS minus VT, and from there onward, at the top of the channel, the voltage will remain constant, current will become constant. Any additional voltage will be spent to drag electron to the pin stop region. So now, if at the saturation region, drain voltage becomes equal to this, so what I am having here, in saturation region, then current ID will be
Square.
VGS minus VT times VGS minus VT. VGS minus VT squared, and this will be VGS minus VT squared divided by 2. As if A square minus A square divided by 2. So it will be in the saturation region, all I will have is VGS minus VT square divided by 2. So this is the saturation current equation or IV characteristics in the saturation current. So, and this is the summary for the 3 regions of operation. Current ID will be 0 if VGS is less than the threshold voltage, because at that time MOSFET is off, no channel will be there, so it will be off. But in the linear region, first condition we have to make that we have to turn on the transistor by making VGS greater than threshold voltage. Channel has to be formed. Then, for any drain voltage less than this, MOSFET will be in linear region and the current voltage relation will be guided by this equation. And at VDS minus VGS equal to saturation, it will enter into saturation region. Beyond that, it will be this pinch off. Beyond that, it will be in saturation region. At pinch off, of course, threshold gate voltage has to be greater than threshold voltage. Drain voltage should be equal to or greater than this. So then, this will be our current equation. Yes.
Can you go back up to that last slide? On that, trying to figure out, so that VD sat by 2.
Yeah. So,
Math right
because,
where did that go?
okay.
Yeah.
So, in saturation point, drain voltage becomes equal to VD sat.
Right.
Drain saturation. And that voltage is VGS minus VT.
Yes. Yeah.
So, in saturation region, I am replacing VDS with VD saturation.
Yep.
But we know that this value is equal to VGS minus VT. So, on the left side, what we have? VGS minus VT times VGS minus VT.
Yep.
Minus, this is VGS minus VT whole square divided by 2. So here, A times A square, here minus A square divided by 2. So what I have left? A square, half A square. So VGS minus VT square divided by 2. Yeah.
In PMOS condition, current will be negative, positive because of
Yeah.
poles, right?
Yeah.
And electric field will also be positive.
Yeah.
So
why
the equation
don't-
will be same, right? For current ID.
Yeah. So let me write, did I write the equation here for PMOS?
In 30.
No, I just wrote the condition. So let me write the equation for PMOS. That would be actually easier for all of you. So, somebody sent me an email before next class to bring some good marker. Yes. So, in that case, current ID for PMOS. ID for PMOS will be 3 region cutoff when VSG is less than VTP, its cutoff ID equal to 0. Right? Now, linear. In linear, first of all, VSG must be greater than equal to VTP, actually greater. And then the condition is VSD, so it has to be
Yes.
less than VSD minus VTP. Right? So current equation will be just exactly, so let me write it here. So the current equation will be for linear PMOS. First of all, so the current equation ID will be mu n will become what? Mu b. No, this minus is a constant thing. And COX WL, but it will be WL of P, right? And then times, instead of VGS, it will be VSG minus VSD, right? VSD, sorry,
VT, magnitude of
Sorry.
VT.
VTP minus VLSI square divided by 2. This is the linear current equation, right? So now here for PMOS, VDS set saturation will be what? VSD minus VTP. So
This is for NMOS, right?
this is for PMOS.
PMOS.
P, VSD. So what so this we're talking about PMOS. We converted to magnitude. DS becomes SD. GS became SG. Mu N becomes mu P. This we'll be talking about the width over L ratio of PMOS, right? And for saturation, first of all, VSG is greater than VTP, right? And then the VSD must be greater than equal to VD set, which is equal to VSG minus VTP, right? So for that, current ID will be mu P COX W
L by 2.
2L, right?
Yeah.
It will be VSG minus VTP magnitude square, right? So yeah, so I want you to write those equations at home side by side. So typically in some literature what they do, they put a subscript n here to just to make sure that you can distinguish the two equations. It's up to you. Okay. So these two, again, spend some time on these slides. And this is basically graphical representation of these two equations. Initially, it is showing linear. As the square term becoming dominant, it tends to saturate. This curve is where pinch off takes place. And beyond that, current becomes independent of drain voltage, that is saturated. But since in the saturation region, current has a square dependency on gate voltage, current jumps from one gate voltage to that voltage quadratically. So this is the ideal voltage transfer characteristics of it. So once again, slide number 18 to 34 or 35, spend a lot of time to make sure that you understand the MOSFET characteristics very clearly. Question?
So I have a question.
Yes. Yes, yes, yes.
For ID, compressor,
Form or SD form, then we have to worry about the current polarity. But here, we have already taken the voltage polarity into consideration because the voltage polarities are opposite for PMOS. Same level of unit.
Okay.
Like if you want to do everything in centimeter, because this mobility is given in centimeter square voltage per second, everything is voltage. If you want to do final calculation in terms of centimeter, you have to convert that channel length L and this oxide thickness W into centimeter with appropriate weight factor.
To nanometers, like what the process is, or centimeters?
Okay,
So 1 angstrom is 0.1 nanometers.
So here you want to calculate the shown it. First thing you have to, for that given drain voltage, is it in linear or saturation?
So 1.2 is gonna be linear.
1.2 will be linear because gate voltage is 1.8, threshold voltage is 0.4, so 1.4, so it is in linear. For 1.6, it is in saturation.
So ideally,
So you know which equation to use here, which equation to use here. Now, in this equation, mobility is given COX is not given. COX, you have to calculate. COX you have to calculate. COX is per unit area capacitance. Per unit area capacitance is given by epsilon over TOX. Per unit area capacitance, where is that? Per unit area capacitance is EOX over TOX. That is per unit area capacitance. Per unit area capacitance is EO. So we have to know the oxide permittivity, right? So now,
So you can't find COX in this question, right?
gate oxide thickness is given. Gate oxide thickness in this equation, what do you need? You need mobility, you need gate oxide thickness and EOX to calculate, you need W over L ratio that is given, that's a ratio. You know the voltage, you know the threshold voltage, you know the gate voltage, you know the drain voltage. Only thing here, I have intentionally did that. There is one thing missing in this. What is that?
Permeability of silicon dioxide, right?
So you have to find a way to derive it, or you can just do a simple Google search here, because silicon permittivity, silicon dioxide permittivity, that is a constant at room temperature. But you can write the answer in terms of sum factor multiplied by UX, that's fine, right? So you see, I want you to think, there is one factor missing. You have to apply this equation directly as it is. There is one factor missing, because COX is UX over TOX, right? So I'm not going to give you everything as it is needed. So you have to think what is you see here. WL is given.